Here is our first identity that we will be using. Sine alpha plus beta. Sine alpha plus beta. Anyone remembers this first identity? Sine alpha cosine beta plus sine beta cosine alpha. Sine alpha cosine beta plus sine beta cosine alpha. So, therefore, I continue. Writing limit as h approaches 0 from sine x cosine h plus sine h cosine x minus sine x, everything divided by h. Okay, so now let's look at these three terms. And I know I can factor out from two of those, not from all, unfortunately, or fortunately, whatever you want to say. So I could factor out something from two of those. Perfect. Sine x cosine h minus 1 plus sine h cosine x divided by h. Here is our second trig identity that we have to use. Number 2. Sine squared h equals 1 minus cosine twice h divided by 2. I should have used alpha not to confuse you with this. It's the general formula. So anyway, but it's the same thing. But I really wanted to stick with alpha and beta, but I looked at this and I wrote h. So that's okay. Okay, so from here, you can say, how is this related to anything in a moment? So I'm going to cross multiply and write that 1 minus cosine twice h equals 2 sine squared h. You can say, okay, you're getting close. So I see now some sort of connection. 1 minus cosine minus 1. So I'm thinking that you are triggering this piece, and you will be correct. However, see, this is a double angle, and this is the angle. Well, I don't have a double angle here. So these identities are to be looked at in a, if you want, dynamic way, meaning if this is h, then if this is 2h, this is h, and if this is h, then this is h over 2, right? If I have here 10, then I have here 20. 10 and 20, because it's double angle. If I have here 1/2, then I have here 1. So, but I need cosine h minus 1, so I need 1 minus cosine h. So I'm going to factor out -1 eventually, but I'm working on this for a moment. Just to refresh your memory where this is coming from. So I have then, you will either factor out -1 here or just multiply both sides by -1 here. It doesn't matter. So I have cosine h minus 1 equals -2 sine squared h over 2. Once I change this into h, I have to change it into h over 2, because this is the double angle. Whatever this is, this must be double. So obviously I'm going to replace all this piece by this. We're not far, but it's not a one-step proof. Okay, limit as h approaches 0 from -2 sine x sine squared h over 2 plus Don't write the rest because I need to show you the third identity that I need to use. And that is sine twice alpha, which is 2 sine alpha cosine alpha. I am now, of course, triggering this. So you can say, wait a minute, this is sine twice alpha and this is sine h. Yes, because I can change the double angle into angle, and then the rest changes into half an angle. So I'm replacing this by this, of course, with h over 2 and h over 2. So plus 2 sine h over 2 cosine h over 2 times, of course, I ran out of room, cosine x everything over h. Now I can factor. Please tell me what we can factor at the top. So see, in this situation, I always said, oh, the difference quotient, yes, very easy. You just make sure that all terms without h cancel each other out, and then you simplify the h. Not for this function though. So I will factor out a2 or negative 2. You will factor out that sine h over 2. Awesome. And what is left? The negative 2 is outside. One of these two signs is outside, so I have sine x sine h over 2. Then minus 2 is out. Sine h over 2 is out. I have cosine h over 2 and cosine x. And I promise this is the last identity. Number 4. Which will replace all this. So number 4, cosine alpha plus beta. Cosine alpha, cosine beta, but minus sine alpha, sine beta. Yes, it's twisted. So I'm going to just multiply by -1 or just put the negative inside there. Cosine h over 2 cosine x minus sine x sine h over 2. So combine this with a minus. Almost there. So limit as h approaches 0 from 2 sine h over 2 over h cosine h over 2 plus x or x plus h over 2, it doesn't matter. Okay, one last step. When h approaches 0, where does this piece go? Just that piece, and then we'll address the rest in a minute. Exactly. Good. Let's see the rest. We know that this piece approaches cosine x, but now let's see the rest here. I am going to change sine h over 2 with 2 in front by putting the 2 here in the denominator. I'm not going to correct it here. I'm just going to write it one more time. So I want this. Limit as h approaches 0, sine h over 2 over h over 2, because when I flip this, I get 2 over h. Right? It's just a simple algebraic manipulation. When I divide by a fraction, I flip. Multiply by cosine x, which, by the way, does not depend on h. I could have taken cosine x right in front. And I'm going to do it, but just to make sure that you understand that cosine x does not depend on h anymore. Okay. A few minutes ago, we looked at the limit. Okay, I'm sorry, an hour ago. We looked at the limit. And here's the limit. As long as this piece, and this piece are all the same, and the piece of this x approaches 0, what do I have in my situation? I have this. Limit as h approaches 0 from sine h over 2 over h over 2. But when h approaches 0, I hope you agree h over 2 also approaches 0. What should this number be?
1.
Yes, because they are all the same. I'm going to talk about this again right after we finish this. So then, what is this approaching again? And the derivative of sine x finally is? So coming back to our list, now we can fill it in. This is cosine x. And this will be negative sine x. And let's determine, this we cannot, these two we cannot determine just yet, unless we use the quotient rule. Yes, we can. Okay, we can use the quotient rule. I wanted to use the chain rule, but we don't have it yet. So we can determine any of these by hand, and then I'll give you the rest. You want tangent, cotangent, it doesn't matter. Which one?
Tangent.
Tangent. Okay, so let's determine tangent, but in the meantime, let me write the rest. So this is negative cosecant squared x. This is secant x tangent x. And this is negative cosecant x cotangent x. So we just want to come back and put in the answer for tangent after we determine it by hand with differentiation rules. I'm not going to do this again with a definition. No, don't get scared. Promise. Okay, so we want to determine the tangent prime. That's not a big deal at all, because this is sine x over cosine x prime. And I'm going to use a quotient, the quotient rule. When the top prime is sine, now I know when I differentiate sine, I get cosine multiplied by the denominator minus the numerator times the denominator prime. We didn't determine this one, but I gave it to you, is negative sine x divided by cosine squared. Can anyone simplify a little bit the numerator and tell us what it is? So it's cosine squared plus but what do we know about this? Exactly. This is another identity. That equals 1 over cosine squared. But we know what trig function is 1 over cosine. Secant squared x. And now we have the entire table of derivatives of trig functions. So secant squared x.
Guessing you strongly recommend.
Say it again.
You strongly recommend that we memorize all this.
You will without even wanting to, because you'll have a lot of examples and a lot of problems to work on. Yeah. So it's a very good question, actually. So now tangent and secant squared, cotangent and negative cosecant squared. So cotangent starts with c, cosecant squared starts with c, but it's negative. The last two are a product. Secant, as you see, secant tangent. Cosecant, as you see, they are together. Negative cosecant cotangent. So if you remember tangent prime, then you should remember that the secant is a product secant tangent. But the other one with negative, because the cotangent prime is negative cosecant, so it will save you a lot of time if you remember these, and you will eventually. Okay, so we want to pick some differentiations, and then I would like to talk about that limit again, the sine x over x. So as you see, they're also showing the same thing. They're asking you to do the same thing we just did for the tangent. Okay, so let's choose a differentiation from here, anything you'd like, to practice the derivatives of trig functions. And then I would like to look at these limits. Yes, we can get away from limits. Calc 1, Calc 2, and beyond, you can get away from limits, sorry. And I put some of these on the handout that I gave you. Okay, so which function we would like to look at and differentiate first? 15, the x e to the x cosecant x. So 15 on page 197. So f of x, x e to the x cosecant x. Well, we have never seen something like this before. This is very unique. How come? Well, we don't have a rule, we do. But we don't ask you to remember the rule for three functions. So I have to split them in two. So this will be my first function, but it's a product, and I will have to apply the product rule. And this will be my second function. So let's write it step by step, and then we'll go back and fill it in. So very good pick, thank you. So remember the first function prime, I have to write x e to the x, but leave it alone and put prime on it. Copy cosecant x plus x e to the x, but now you have to differentiate cosecant x, which is, it's among the last two, so it's a product, right? So minus cosecant x cotangent x. There is nothing you can do to the second term, but we have to use the product rule again, as this one being 1 and this one being 2. So the first function prime is 1, e to the x plus x times the second function prime, which is e to the x. Now, eventually, I will distribute cosecant x, and this is negative x e to the x cosecant x cotangent x. You could factor out e to the x or not, just write e to the x cosecant x plus x e to the x cosecant x minus that whole thing. So basically, you do not have to memorize this. I'm not going to ask you to do any of this. But when you have a function times the second times the third prime, you get the first times the second times the third plus the first times the second prime times the third plus the first times the second times the third prime. There is no need for a formula like that. None whatsoever. Well, that's the idea. That's exactly what happened here. They may not be exactly in this order, but that's exactly what really happened. Okay, so now let's look at these limits. Again, we already talked about this limit. It needs to be, again, we already applied it. It needs to be looked at like this. as long as these three pieces are identical and it approaches 0. So you understand that everything I write like x approaches 5, it's the same thing with x minus 5 approaches 0. If I write x approaches negative 3, it's the same with, yes, that's it. Exactly the same thing. So I would like to practice this, and you'll tell me which function. I would like to start with the very last one because it's a perfect example. I like to start with 48, and then I'll let you choose whatever else you would like. Is that okay if we start with 48? Okay. Because it's such a good example for what we're trying to do. Okay. So 48 on page 198. So limit as x approaches 1 from sine x minus 1 over x squared plus x minus 2. Bless you. Yes, of course, you can say just if it's 0 over 0 or infinity over infinity, use L'Hopital's rule and you're done. I can't just yet because I have not presented the chain rule to you, so we don't know how to differentiate sine x minus 1 yet. It's a function of a function, so we don't know that yet. It happens that it's not going to be anything different, but that's okay. I'll present that hopefully maybe tonight. Okay. So when you plug it in, what do you get? Very good. So this is basically, you can put it in parentheses, x minus 1 approaches 0. Same thing. Either x approaches 1 or x minus 1 approaches 0 is the same thing. What do you think I'm going to do next? Yes, of course. You know me too well already. So the denominator is definitely, it must have a factor of, and I know that and I know why. Right. If it doesn't have a factor of x minus 1, it would not be 0 when I plug in 1. Very good. By the remainder and the factor theorem. Yes, awesome. And what is left in parentheses? And now please remember this. Where is this going? Yes. And what is the limit? Over 1 over 3. 1 over 3. Very good. And this was possible because of this. Any questions? Okay, now feel free to choose any limit you like. 45. Very good. (45) on the same page, we have a limit as x approaches 0 from sine x squared divided by x. Again, we cannot use L'Hopital's rule because we don't know how to differentiate a function of a function. Okay, then. Good. So there is nothing I can do. I don't want you to get confused here. So there is nothing I can do to sine x squared. I can simplify. I cannot do anything. I can't touch it. So obviously this time I have an x squared that I need to worry about, and there is nothing I can do. So the denominator has to be the same. No, not a problem. I can multiply by x and divide by x, or multiply the top and the bottom by x. Now I got this. And I hope you agree that when x approaches 0, it's the same with saying x squared approaches 0. So by simply manipulating the function a little bit without changing the value, just the outlook, just the presentation, I multiply the top by x and I multiply the denominator by x. I'm allowed to. It's not 0. X approaches 0. It's not 0. I created exactly what I wanted. What am I talking about? I want this and this and this to be identical. And then where is this going then? Because all these pieces are identical. 1. But x approaches 0. Don't forget I have an extra factor here, and the answer is x is in the numerator. The x squared was in the denominator. Numerator, denominator, x squared approaches 0. Exactly. This is x over 1. Excellent. That is 0. Because this was in the numerator, not in the denominator. So I multiplied the denominator by x and the numerator by x. The denominator became x squared because that's what I need. This is carved in stone. I have to have the same quantity no matter what it is. So then the answer is 0. Any questions? Is that okay? Okay, I think we need to choose another at least one before we continue. Oh, you chose 45. I wrote 46. Okay, I'm sorry. I'm gonna. No, I'm sorry. I'm gonna do 45, but I also would like to show at least 40 or 41. It doesn't matter. So yes, I'm so sorry. I'm sorry. Yes, you did say 45. I copied 46. So let's do 45 and 40. Is that okay? Okay. I promise I'll copy 45 now. I don't know why I copied 46. I know the difference between 45 and 46. So limit as theta approaches 0 from sine theta over theta plus tangent theta. I love this one. Thank you for picking that. Okay, so what do I do? Yes, I plug it in first. Here I didn't do it, and I should have. It's 0 over 0, of course. I did it here, but I didn't do it here, so I'm sorry, I jumped. Good, so when you plug in 0 at the top, you get, when you plug in 0 in the denominator, you get, perfect. But 0 over 0 is a theorem that we, or a rule that we just looked at, and I want to apply it. Because there is no function, bless you, there is no function inside a function. So what do I write? So the derivative of the top is, because now I know what it is, cosine theta. The derivative of theta plus the derivative of tangent theta. Secant square theta. Okay, let's give it a shot again. The numerator goes to, yes, the denominator goes to, remember secant squared is 1 over cosine squared. So if cosine is 1, then 1 over 1 will be secant squared. That's it. It couldn't be easier, right? With L'Hopital's rule. But please do not ever get confused and see a quotient and say, oh, it's very easy. I differentiate the top when I differentiate the bottom. No, no. Please don't ever do that, right? Only inside a limit, and only when you have 0 over 0, you are allowed to do that. If there is no limit, you cannot use anything else but the quotient rule, right? Okay, perfect. So I was looking at 40. So we have limit as x approaches 0 from sine 4x over sine 6x. No, on this one we cannot use L'Hopital's rule. It's very simple with L'Hopital's rule, but we don't know the chain rule just yet. That will be our next step. The chain rule is the next section. That's what we're going to do next. So where does this go? The top and the bottom? Yeah, but I cannot use L'Hopital's rule. Good. So a very simple algebraic manipulation. I hope you agree that when we look at x approaches 0, we really mean 4x approaches 0, and we also mean 6x approaches 0. No doubt, right? If x approaches 0, 4x and 6x both approach 0. Agreed? Perfect. Okay, so I do have this. What do I need in the denominator, though?
4x.
No problem. I multiply the denominator by 4x. As long as I did the same thing to the top, that's 1. I didn't change anything. Okay, now for sine, I did not mention that, but I would like to go back and write it here. Also, the multiplicative inverse will give us also 1. So limit so if it's sine x over x or x over sine x, the same thing. Okay, what am I missing then with sine x? Sine 6x. As long as I multiply the top by 6x and the denominator by 6x, I'm really multiplying by 1. I'm not changing anything. But now, of course, I'm going to ask you, where is this going? And also, where is this going? And what is the limit? By a simple algebraic manipulation of the function. 2/3. This approaches 1, this approaches 1. X from the top with x from the bottom go away. 4 over 6 is indeed 2/3. Well done.
Are you determining 1 just by simply dividing 4x divided by 4?
Yes, I simplified x by x, and 4 divided by 6 is 2/3. Yes. Yes. Because I didn't need, I can simplify before I apply the limit. 3.4, the chain rule. What is the chain rule? We're trying to differentiate something like this, which is a function composition, which by definition equals f of g of x. So we really want to differentiate a function of a function. And here's how we do it. This is the inner function, and this is the outer function. The order is not important, but we prefer to say that we differentiate from outer to the inner. When we evaluate a function, we evaluate the inner and then the outer. When we differentiate the outer first and then the inner. It's going to be a product. It's not going to make a big difference because 2 times 3 is 3 times 2. But I recommend keeping that in mind. So I differentiate the outer function of g of x, and I multiply it by the inner function prime. So let me say again, this is the inner function. This is the outer. This is the first function that is applied to x. That's why it's called the inner. And this is the second function, the outer function applied to g of x. Okay. I sort of lied to you. When we differentiated this, to be fully honest, I should have written, give me the beginning, but I should have done this. But I didn't. Why I did not write x prime, which is, if you want, the inner function prime, because x prime is 1. That's why I didn't. So now when I differentiate a function raised to power n, this is a chain rule. The inner function, the outer function. When I evaluate this, I will have to evaluate f first. I get 15, and then I raise it to the 10th power. So according to this, what should the formula be for a function raised to a power prime? Inner, outer. But now this is no longer 1 times f prime. This is the chain rule combined with the power rule. What do you think about the following? E raised to 2x squared minus 3x prime. What do you think this equals to? If I only have e to the x prime, I have e to the x. But now I have a function. This is not x. What do you think this will equal to? E to a function prime. E to the function times, so I should write here times x prime, but I didn't because it's 1. But here I have no choice. Exactly, times f prime. So this is e to 2x squared minus 3x and multiplied by 4x minus 3. Exactly, because that is not x. If it were x, then x prime is 1 and I'm done. But it's a function of x. Any questions? We have to practice at least one rational function, mandatory, because you're going to see in chapter 4 why, and anything else you'd like to choose to apply the quotient rule. I'm sorry, quotient rule combined with the chain rule, or product rule combined with the chain rule, or just simply the chain rule. Which one? Best you two. You said, I'm sorry?
26.
I was sneezing and I couldn't see. Okay, yes, we'll start with 26. That's a very good question. So 26 on page 205. So I'm going to use x instead of y just for simplicity. So x minus 1 to the 4th power, maybe for convenience more. To the 5th. I think it's the 5th, isn't it? Yes. Well, this is a big deal. This kind of problem is a big deal for the next chapter. Okay, g prime of x. You know I'm going to run out of room, so be prepared. So this function is number 1 at the top, and this function is number 2. I have to differentiate the numerator. I have to use this formula where I have 4 times x minus 1 to the 3rd power times x minus 1 prime. It happens that x minus 1 prime is still 1, but so I have 4 x minus 1 to the 3rd times the inner function prime, but there is no need because it's 1. Now I copy x squared plus 2x to the 5th minus, so this was the first function prime times the second one minus the first function times, can anyone give us the denominator prime? Slowly. Yes. 5 times x squared plus 2x to the 4th times the inner function prime. 2x plus 2. So forgive me, but it should be here. Over the denominator squared. When I raise the denominator to the second power, I get x squared plus 2x to which power? To the? So when I square this, I copy the base and I multiply the exponents. Excellent. Be very careful. It's tempting, but please, please don't get tempted to simplify these two. Because this is not a factor at the top. This is part of a term. You have to wait till we completely factor the numerator and then we can simplify, but not before. Okay. Can anyone tell us how many terms we have in the numerator? It's the quotient rule. We have to have only 2. We can't have more unless one of these is a product, and then yes, it can be anything else. But at this point, we only have 2 terms. Here's one, and here's the other. So, can anyone tell us what we factor out from top terms? Yes, which power? Indeed, the smallest of the 2. Great job. What else?
X squared plus 2x, 4.
Indeed, 4 and 5, the smallest. And then I have x squared plus 2x to the 10th. And now we have to be very careful what is left in brackets. From the first term, there is a 4 left. This is completely out. And from 5, I pulled out 4 of those. Then one of them is left inside. Do you agree? Then we reach the negative sign. A 5 is left. From x minus 1 to the 4th, we pulled out x minus 1 to the 3rd, but still 1 is left inside. X squared plus 2x to the 4th, happily out. Nothing left in there, but I still have a 2x plus 2. 2x plus 2. I hope you're proud of me. I kind of ran out of room, but not exactly. I was able to squeeze it in. Okay, now I'm super, super happy. Only now I can simplify because I'm simplifying factors. So then x minus 1 to the 3rd, x squared plus 2x to the 6th, and I distribute 4x squared plus 8x minus. Here's how I would like to, this is how lazy people multiply. So we have 5, I have x minus 1 with minus in front, and I have 2x plus 2. I hope you agree with this. Agreed? And then you agree with this. This times this is x squared minus 1. And then you agree with this. That's how lazy people multiply. They don't multiply these two and then distribute -5. They just find a way of doing something like this and making it easier on themselves. You don't have to do this, of course. But it will take a little bit longer to multiply those three factors. Okay, the final simplified form, x minus 1 to the third, negative 6x squared plus 8x plus 10. And of course, you know I'm going to factor out -2. I could also simplify a little bit the denominator by factor out to x, but that's okay. So x minus 1 to the third. Oh, of course, -2. X minus 1 to the third. And 3x squared minus 4x minus 5 over x squared plus 2x to the sixth. Yes, it was very painful and very long. You're not going to get something like this, but you're going to see where it comes into play in chapter 4. And why we need to painfully go to the simplest possible form. You will see that. So it's 3x squared minus 4x minus 5. Any questions? And I forgot to mention, I replaced the lowest test grade with the final exam grade, so everyone can still get an A in the class. I hope I mentioned that before. Okay? As long as there are many A's in the class, but a couple of students could have done better. So everyone can still get an A in the class. And I hope you do, please, for me. Okay, so let's choose another. I would like to look at something like this because I think you're going to have something like this in WebAssign. Maybe something like this. And then I would like to, if I have time today, I know I have 15 minutes left, I'd like to look at something like this. But I haven't presented the rule yet for that. So just choose anything else. I'd like to look at this because this is a very important type of problem first. Okay, so 36. So then y equals the square root of 1 plus x e to -2x. Although it doesn't look difficult, I just want to say that it needs attention. Remember when we differentiate in the square root of x, this has to be embedded in our system by now. Okay, for the same thing, please just tell me what is f, the square root of a function prime then. Remember, I should have put here times x prime, and I didn't because there is no need. So now please tell me what we have when we differentiate a function raised to 1/2 or the square root of a function. Exactly. Same formula, everything the same, but because it's not x, x prime is 1, I have to multiply by the function prime. Okay, perfect. So now this is my function, and this is the square root of the function. I'm using this. So please dictate. Times the inner function prime. When I differentiate 1, what do I get? 0. But now I have to differentiate a product. So times the first function prime, e to -2x, plus the first function times e to -2x prime. The power is not plain x. I have to treat it as a function, as -2x. So times e to -2x multiplied by the inner function prime. Very good. Okay, let's try and simplify a little bit. What do you think I'm going to do here? Yes, e to negative 2x. And then I have 1 minus 2x over 2 the square root of 1 plus x e to negative 2x. You could bring this down if you wanted to. And this is final. Any questions? This is okay. Okay. 41 that I promised, f of t equals sine squared of e raised to sine squared. Some of these are kind of weird. Not weird, but taken to extreme. We want to determine f prime. Ready? How many functions we have here? And you can say plenty. That's the most outer function. That's the next one. Then e to this. Then sine squared. But basically power 2 and then sine. 1, 2, 3, 4, 5. When on this kind of function, a function inside a function, when you apply the chain rule, make sure there is no addition or subtraction. Right? Why? Look at the chain rule. Whatever times whatever times whatever times whatever times whatever. There is no addition of terms. You only have a big product. So please notice that. Okay, then we are going to consider the function squared. So first I differentiate the power. Everything is one thing. This is just one function, but it's taken to a second power. So this is the inner, but it's composed of 3 functions, right? This is the inner, the power is the outer, and then sine. I have to start with the power. What do I write? 2. From 2, I subtract 1, so 2 sine e to sine squared t times the inner function prime. 2, one more time, 2 sine to 2 minus 1 times the inner function prime. But when I differentiate sine of whatever, what do I have? Yes, times cosine of e to sine squared t, and times. I haven't even gotten to this function. Now I am ready for this. One more time. 2 minus 1 times the inner function prime times the inner function prime. I differentiate e to a function. What do I get? E to that function times the inner function prime. But it has a power. So it's 2. It's sine to 2 minus 1 times the inner function prime, which is cosine t. As mentioned, 5 functions. Yeah, I know. Let's do this one more time. So I have a function to a power that I need to differentiate. So I differentiate the power, bringing the power in front and subtracting 1 from the power, and I have to copy the rest. now times the inner function prime. So 2 times sine times the inner function prime, which is this. Agreed? Times, and finally I'm here. I'm differentiating this. Well, e to a function prime is e to a function times the function prime, sorry, 2 sine x times the inner function prime. I can't do anything other than just multiply these two and write 4 and copy the rest. I like to put this first. These and these two. Nothing you can do here. Don't even try. And this is it. Any questions? One quick application, I promise, and I'll stop. Last problem. We have not completed 3.10.4. I would like to look at some other applications here, but I like to look at the rumor application. I like the rumor. We're not going to have to graph. It's a graphing calculator. I just want to answer part A and B. Okay, so we have, under certain circumstances, a rumor spreads according to the equation. F of t is the proportion of population who knows the rumor at time t, at a and k are some positive constants. In section 9.4, which is in Calc 2, that's something else. They're going to talk about this function. So then the limit as t approaches infinity of p of t. So what happens if time goes by? What happens to p of t? What will be the percentage of people who hear the rumor? And then find the rate of spread of the rumor. What does that mean, the rate of spread of the rumor? Of course, yes, p prime of t. Very good. That's it. So this is 84 on page 207. And this is p of t, which is 1 over 1 plus a e to negative kt. And the first question, so this is percentage or proportion. Let me write proportion. And t is time. And a and k are positive constants. So they want us to determine the limit as t approaches infinity from 1 over 1 plus a e to negative kt. So let's do this together piece by piece. If t approaches infinity, where is this going? Good. Where is this going? If the numerator, careful. So e, yes, 0, right? How much is a times 0? And how much is 0 plus 1? How much is 1 over 1? So 1 or 100%, right? Everyone will hear as time goes by to infinity. Okay, final step. I just want to determine p prime. I'm not going to use this. Of course not. I'm going to use that. So p prime of t. We bring down the power, which is, we copy 1 plus a e to negative kt to which power? Very good. Times the inner function prime. A is a constant, K is a constant. How much is 1 prime? So it's A e to negative kt times the inner function prime. Perfect. Okay, A negative k with minus in front. This has power negative power. And this has a negative power. This is the rate of change of rumor.